Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at the Laplace's expansion theorem, and this is going to be one of the applications of the first discussion we had on minors and cofactors. Now, in this case, we're going to look at this specific aspect of a theorem, and it's going to give us one of the strategies that we're going to use in obtaining a determinants. And this, of course, is going to be a convenient way for trying to figure out how we can find perhaps a determinant of an array of matrices. And of course, we're going to see that this basically is going to be applicable, especially when we have already known how to determine the minors and cofactors of our determinants. Now, in this case, I'm going to give a specific illustration for a particular matrix. And of course, this is going to be the similar example that we had used in our first discussion on the concept of minors and cofactors. So I'm going to put a link of that one in the description box, and we're going to make a few corrections from the first one that we have done in terms of the minors and cofactors. So in this case, basically, this is a form of a theorem, and this theorem states that the determinant of a matrix A, which has got an element of given as Ij, which is a ith row and jth column, can be determined or is equivalent to the sum of the product obtained by multiplying elements along n row of their respective cofactors. And of course, this one can be given in terms of an algebraic expression, whereby we are going to see that for us to represent the determinant of A, this is given in terms of those specific symbols for the absolute value given in terms of A. So this implies the determinant of A given as such. So the determinant of A can be obtained from the Laplace's expansion theorem, which states that the determinant of a matrix of this specific form is equal to the sum of the product obtained by multiplying elements along n row of their respective cofactors. And of course, this can be obtained by giving one of the examples that we had used in our first discussions on minors and cofactors. So we had said if we have a matrix which is an n by n matrix given in terms of the first column as 2, 0, 1, and then we're going to have the second column as 3, negative 4, negative 1, and the last column as negative 4, 2, and 5 given as such. So from this specific theorem, we have said that we can obtain the determinant by finding the sum of the product obtained by multiplying elements along n row. So we can have the first row, the second row, the third row, of course, with the elements of any row of their respective cofactors. So we had mentioned and said that basically these cofactors are going to be represented using a general illustration, whereby we have said that if we have a Aij matrix, then its cofactor can be found by this specific element of a negative 1 raised to I plus j, which means we are going to add this specific element of an ith row and jth column, and that one is going to be multiplied with the specific minor over that specific, of course, ith row and jth column given as such. So I'm going to give this specific representation, and of course, from this theorem, we're being told that this is going to be n row of their respective cofactors. Therefore, it's incumbent upon us to find the minors and of course the specific cofactors of this specific representation, whereby, as I said, we're going to find the minors represented in terms of 1, 1, of course this is a 2, 1, and then we're going to have 3, 1. So the first one represents a row and then the column. So this is going to be row 1, column 1, row 2, column 1, row 3, column 1 in that specific order. So I'm going to arrange this array of numbers in terms of the respective cofactors, and then we're going to fill them up. So this is row 1, column 2, and this is row 2, column 2, and this is row 3, column 2, and of course this is going to be row 1, column 3, row 2, column 3, and row 3, column 3, given in that specific order. So this represents the minors of those specific numbers, or the minors of those specific submatrices that we're going to obtain by deleting the ith row and the jth, row and the jth column. And therefore, I'm going to just put them on the board since we had obtained them from our first discussion. I've said I'm going to put a link of this specific video for finding the minors and the cofactors. So in this case, I obtained the minors of 18, 11, negative 10, course this was negative 2, 14, and then this is 4, and then this is 4, negative 5, and negative 8 respectively. So in this case, we had said that for us to obtain this specific, of course, matrix of the cofactors, we're going to factor in this specific number for negative 1 raised to power I and j. So the summation of I, j basically is going to constitute these numbers, and the n factor that you obtained by raising this negative 1 to that specific sum is going to influence of course, various cofactors that you are going to obtain. Now in this case, I'm going to have this one given in terms of the respective cofactors for A11, A21, A2, A31, and then A12, A13, A22, A23, A32, and A33 respectively. So basically this is going to be the minus multiplied by negative 1 raised to those specific sums respectively, and this we're going to obtain of course the cofactors in terms of negative 18. So this implies that if we have negative 18 as a minor, then therefore we're going to have negative 1 raised to power 1 plus 1, which is a 2, which is basically going to be negative 1 raised to power 2 is going to be a positive number. Therefore positive 1 times negative 18 is going to give us this specific number, and those are going to be considered in that specific order. So we're going to obtain a cofactor 2 there, and then we're going to have 4, negative 11, and then we're going to have this one as 14, and then we're going to have this one as 5, 8. So basically this is going to be negative 8, since this one is going to be a positive 1 times negative 8, and then we're going to have this one as negative 4, and then lastly we're going to have this one as negative 10. So this array of numbers can be arranged in terms of a matrix, another matrix, which of course is going to be given in terms of this one. So this is going to be giving a matrix of cofactors, and of course this is going to be in terms of 18, negative 11, negative 10. So that's going to form our first column. The second column is going to be given in terms of a 2, 14, negative 4, 4, 5, negative 8, and this is going to be a matrix of cofactors given in that specific order. Therefore, from the Laplace's expansion theorem, the theorem states that a matrix of course, or the determinant of a matrix A given in this specific case is equal to the sum of the product obtained by multiplying elements along any row of this specific matrix with the elements of any row of their respective cofactors. So we have obtained a respective the matrix of a respective cofactor of A given in that terms of this array of numbers. Then therefore multiplying each specific element of this specific cofactor together with the element of the matrix, the sum of these specific products are going to give us the determinant. So let's check out whether that one is going to give us some kind of a meaning. So we're going to have the first one given in terms of in terms of the determinants. Let's take for the first one. So we're going to take the first row and the first row of the cofactors and the first row of the matrix, which is of course 2 into negative 18. So 2 times 18, and then the sum. So it says the theorem talks about the sum. So it's 2 times 2, which is of course 3 times 2, and then plus negative 4 times 4 given as such. So if we try to look at this specific sum, this is negative 36 plus 6 minus 16, and this is going to give us negative 46 as our determinant. So let's take for the second column perhaps, or the third column together with the elements of the third column together with the elements of the cofactors given as such, and this is going to be given in terms of what? So this is the first column. So for the third respective column, we're going to obtain this one, or perhaps we can still use even the second column and have this one given in terms of 0 into negative 11, and then we're going to have this one as a plus negative 4 into 14. 14, and then we're going to have plus, this is 2 into 5 given as such. So this is going to be 0, and then we're going to have this one 56 plus 10. This is negative 56 plus 10 is going to give us minus 46. So multiplication of the respective elements for the first row and the first row of the matrix plus the first row of the cofactors is going to give us a value, and then multiplication of the second row with the second row of the cofactors is going to give us the same value. So basically this multiplication, of course, is going to give us the third value. Perhaps we can check for the third, of course, let's check for the third row, which is going to be 1 into negative 10 plus negative 1 into negative 4 plus this is 5 into negative 8 given as such. So this is going to be negative 10. So this is going to be plus 4 plus this is going to be negative 40 given as such. So this basically is okay, there's a problem somewhere. Let me check and confirm. So this is going to be negative 10, and this is going to be plus 4, and this is going to be, okay, let me check that one so that there's of course a hitch somewhere. So basically from our summation this should be correct, whereby we have a negative 10 plus 4, which is negative 6 plus negative 4. So negative 6 plus negative 40, this is going to be equivalent to negative 46. So basically this agrees with these two specific laws, and therefore the theorem holds that basically if we want to find a determinant of a matrix of this specific nature, we're going to obtain this specific matrix by the sum of the products obtained by multiplying the elements along the rows of their respective cofactor in that specific case. So basically that's going to form a general case for determinants like the one that we have given on board. So therefore we're going to give a specific general description of this particular theorem, which is a Laplace expansion theorem, given in terms of the determinant of a matrix can be obtained by multiplying the respective elements of a matrix given as that with the matrix, the respective of course elements of their cofactors are given in that specific order. So we're going to have this one given in terms of perhaps we can give them in even numerical value. They don't have a problem with that. So we're going to have this one represented as the element of IA given as such, which is a row times these specific cofactors are given as such, and of course we're going to have the element of 1 or I3 times the row of I3 given in that specific order. So this is going to go on, and then we're going to have this one as the element of AN multiplied by the element of IN given in that specific order. So this is going to go arranged in terms of these specific values, and this of course is going to be plus all the elements in between up to that specific last set. So this one of course is going to be concerning the rows, and of course we can obtain similarly the determinant of this specific matrix by multiplying the elements of A the first one times the jth column times A the first one times the jth column in that specific order, and of course we're going to have this one the second times of course the second times the jth column, A the second times the jth column plus, so that one is going to go in that specific order, and then we're going to have ANJ jth column given in that specific order. So using these two specific representations, we can obtain the determinant of this specific matrix, and this is obtaining or concerning the concept of a Laplace's expansion theorem. So in case we come across it in our subsequent discussion, then therefore it's going to make sense for us that this is going to be the applicable procedure in that put there, and they're going to of course to assist us evaluate other. For now guys, by God bless you. Catch us in our next video.